Welcome to the Deep Dive, the place where we turn often dense research papers into something useful, something actionable for you.
Glad to be here.
So today we're diving deep into a topic that really hits at the heart of, well, scientific progress itself. It's this huge, frustrating gap between publishing really cool research and actually being able to use it, to reproduce it. And our source material today looks at an AI-driven attempt to fix this. We're unpacking something called PaperCoder. It's this pretty clever multi-agent LLM framework
Right.
with a really clear mission: automatically generate a full working code repository just from reading a scientific paper, nothing else.
Yeah, it's all about trying to speed things up,
Yep.
practically speaking.
Yeah.
Because we see these breakthroughs, right?
Yeah.
But then the next step, validating them, building on them, that often just stalls.
Okay, the code's missing.
Exactly. The implementation details, the actual code,
Mhm.
it's just not there. That's the reproducibility crisis right there. It's a massive bottleneck.
And the numbers you mentioned before we started, they really paint a picture. This isn't just a few papers, is it?
Oh, not at all. It's systemic. There was a recent analysis looking at top machine learning conferences in 2024, ICLR, ICML, NeurAPS.
The big ones.
Yeah, the big ones. And on average, only about 19.5%, just under 1 in 5 of the accepted papers actually provided their official code.
Wow. So wait, nearly 80%, 8 TISOY% of the world's top ML papers come out without the code needed to run them.
That's the reality.
Yeah.
And just think about the sheer amount of time. Thousands of researchers globally basically reverse engineering methods from text, just trying to figure out how they did it.
Instead of doing new research.
Precisely. It's not innovation time. It's like forensic documentation time. It just puts the brakes on everything.
Okay, that is a colossal barrier. So PaperCoder steps in. It's trying to be this automated helper, right? A research assistant.
Sort of, yeah.
But we've heard about LLMs generating code snippets before. Why is making a whole repository something that actually runs with multiple files? Why is that so much harder?
Well, it's a completely different level of complexity. Older systems might give you a function, maybe fix a bug in a piece of code you already have.
Right.
PaperCoder is aiming for what they call repository-level fidelity. That means multiple files, all interconnected, dependencies handled, runnable code, and it has to perfectly match what the paper describes.
And the key is it only uses the paper. No looking at existing code.
Exactly. Solely from the paper. No cheating by looking at GitHub repos or anything like that.
Okay, but let's say the paper is written really well. Super clear methods, everything laid out. Why the need for this complicated multi-stage thing? Can't a really powerful single LLM just, read it and write the code?
That's the million-dollar question.
Yeah.
And it turns out it's really, really hard, even for the best LLMs.
Why, though?
Think about how a human reads a paper. You kind of build a mental model, right? You understand the overall structure, how the different pieces connect, the specific details. You hold it all together. LLMs, especially with long documents like papers, they struggle with that global consistency.
They lose track.
They can lose track.
Yeah.
Generating a whole complex modular code base in one go. It often fails because of context window limits or just forgetting a dependency defined 50 pages earlier.
Yeah.
You end up with inconsistencies.
Got it. So PaperCoder mimics how a human might tackle a big project, break it down, like a top-down approach.
Exactly. It decomposes the task, uses specialized agents for different parts of the job. That's how it manages the complexity and aims for that consistent, faithful repository.
Okay, makes sense. So it's a structured process, 3 stages, you said.
That's right. 3 coordinated stages: planning, analysis, and coding.
All right, let's unpack that pipeline. Stage 1, planning. The roadmap designer. Sounds like the architect phase.
That's a good way to put it. This stage is all about translating the narrative of the paper, the descriptions, the arguments, into a concrete engineering plan, like a blueprint.
Okay.
And this stage itself has 4 distinct steps done in sequence.
4 steps just for planning. Okay, walk us through them. Why is each one needed?
So first up is the overall plan. This is high level. It pulls out the main components, the model architecture, how it's trained, the data stuff, how results are measured, things that might be scattered all over the paper.
So the what? What does this project actually do?
Exactly. Then second is the architecture design. Now we're getting into structure.
Like the file structure.
Yep. It figures out what files are needed, what classes should go in them, draws up class diagrams, sequence diagrams, basically the static and dynamic structure, the skeleton of the project.
Okay, skeleton's built. Now, the third part sounds critical, logic design. You mentioned this helps with actually running the code later?
Absolutely critical. This is where the system figures out the order things need to happen in. It produces an ordered file list.
An ordered list. Why does the order matter so much?
Well, think about dependencies. If file B needs to import something, like a class, from file A, you have to generate file A first, right?
Ah, right. Otherwise, it breaks immediately.
Exactly. You get import errors, compilation fails. It's a mess. This logic design step anticipates that and sets the correct build sequence. It solves a ton of potential runtime problems before they even happen.
That's actually really clever. Planning the build order before writing the actual code. Okay, what's the last planning step?
The fourth one is configuration generation. This agent pulls out all those fiddly settings, hyperparameters, learning rates, batch sizes, you name it.
The stuff usually buried in tables or footnotes?
Often, yeah. And it puts them all neatly into a configuration file, like a config.yaml.
Oh, that's handy.
It really is. It means a human user can easily see and tweak the experiment settings later without having to dive into the source code and hunt for them.
Okay, so that's the planning complete. A really detailed roadmap. Then stage 2 is analysis. What happens here? It sounds like zooming in.
It is zooming in. Planning gave us the what and the where. The analysis stage figures out the how for each specific file.
How each file should work internally.
Precisely. It takes each file from the plan and defines its specific job. What are its functional goals? What inputs does it take? What outputs does it produce? What other files does it depend on? What specific algorithms from the paper need to be implemented right here?
So it's translating, say, the math in section 3 of the paper into concrete instructions for a specific code block in model.py.
You got it. It generates detailed specifications for each file, bridging the gap between the high-level plan and the actual code that needs to be written. It's like creating a detailed task list for the coder.
Which brings us to stage 3, coding, the final build.
Right. This is where the code finally gets generated. But crucially, it does a file by file, following that specific execution order determined way back in the logic design step.
To maintain consistency.
Exactly. And for each file, it uses all the context it has gathered. The original paper, the overall plan, the detailed analysis for that specific file, plus any code it's already generated for the preceding files in the sequence.
So it's constantly aware of the whole project as it builds piece by piece.
That's the idea. Build iteratively, stay consistent, follow the plan.
Okay, that structured approach sounds incredibly robust, at least in theory. But the proof is in the pudding, right? How did PaperCoder actually do when they tested it on real papers? Did the code, run?
Yeah, they put it through its paces. Rigorous testing on big data sets. They created their own benchmark called Paper2Code Bench with 90 recent ML papers and used an existing one too.
What were the big takeaways? Did this fancy multi-agent thing actually beat simpler approaches?
It did, substantially.
Yeah.
It outperformed strong baselines, systems like ChatDev and MetaGPT, on pretty much all the metrics.
Okay, metrics are one thing, but did it actually help people?
That's where it gets really interesting. They did human validation studies. They got experts, often the authors of the original papers, to look at the code PaperCoder generated.
And what did they say?
Get this. 92% of those experts said that generated repositories were genuinely helpful for trying to reproduce the paper's results.
92%. That's huge. The original authors found it useful.
And 88% of the time, those experts rated PaperCoder's output as better than the code generated by the baseline systems.
Okay, that's compelling validation. People who know the work best are saying, yes, this helps.
And there was another really key finding, almost a side benefit, but important for the field. They looked at how well the system performed when judged with the official author code versus without it.
How do you mean? Like comparing the AI's code to the ground truth versus just judging it based on the paper description?
Exactly. They found a strong positive correlation, a Pearson R, of 0.79 between those two types of evaluation.
Whoa, okay, hang on. A correlation of 0.79, that's pretty high.
So you're saying the LLM is getting good enough at evaluating code quality just based on the paper, that its judgment aligns closely with what you find when you actually have the ground truth code to compare against.
That's what the data suggests, yeah. It implies that we might be able to reliably assess the quality of AI-generated code repositories using reference-free methods, basically, just the AI reading the paper and its own output. That's massive for scaling things up. You wouldn't always need the original authors or their hidden code to know if the AI did a decent job. The AI could potentially check itself, speeding up development cycles.
It's a very promising sign for LLM evaluation, definitely.
Okay, huge finding.
Yeah.
Let's circle back to the main goal, though. Executability. Getting code that runs. How close did PaperCoder get? Did researchers still have to spend hours debugging? Because that's what we want to avoid.
They got remarkably close, like surprisingly close. They measured this carefully. When the generated code did have execution errors, and it wasn't that common on average, only 0.81% of the total lines of code needed a small tweak to get it running.
Wait, less than 1%, 0.81%. So out of maybe 1,000 lines of code, you might have to change like 8 lines.
On average, yes.
Yeah.
Usually very minor fixes.
That's incredible. That basically eliminates the reverse engineering burden.
Yeah.
If you can get a complex research project running with maybe 1 or 2 tiny fixes, that's a game changer for replicating results quickly.
It really points to high algorithmic fidelity. The system understood and implemented the core method described in the paper extremely well.
And what were those tiny errors usually? Was it getting the logic wrong?
Mostly not, actually. The most common errors were things related to the environment or packaging. A missing dependency it forgot to list, an import error, maybe needing to update a call to a library that had changed slightly.
So plumbing issues, not fundamental design flaws.
Exactly. More like setup friction than deep algorithmic mistakes.
Okay, so near perfect on the core method, but was there any part where PaperCoder consistently stumbled, despite all the planning? A weakest link.
Yes, there was. And honestly, it tells us less about the AI and maybe more about the papers themselves.
Oh, what was it?
When they broke down the analysis, implementation coverage for the core method was great, like 86%. Coverage for the evaluation part was also strong, 79%.
Okay.
But coverage for data processing, that only hit 56%.
56. Hold on. The AI can perfectly code up some complex new model architecture, structure the whole project right, but it struggles with just loading the data.
That's what the results show. And it really highlights a known issue in research papers, doesn't it?
That researchers often don't describe the data handling part very well.
Exactly. Those crucial details about data formats, the specific pre-processing steps, how data gets cleaned or loaded, they're often just glossed over or underspecified in the paper. So the AI can build a perfect engine, but if the instructions for the fuel line are vague, the car won't start.
The AI is only as good as its input, the paper.
In this area particularly, yes. It reveals that gap in human documentation.
So, wrapping this up then, what does this all mean for you, the listener? PaperCoder is a fascinating look at how structured AI, these multi-agent systems, can really tackle big problems like reproducibility. It's like an automated research assistant that can follow complex instructions incredibly well.
It definitely shows the potential. But it also acts like a diagnostic tool for science itself, doesn't it? It works brilliantly when the paper is clear and complete.
Yeah.
But it flags where we, as researchers, often fall short, especially around those messy, crucial data details.
Which brings us to a final provocative thought for you to chew on. If these AI systems like PaperCoder are getting so good they can implement complex methods almost perfectly, but they keep hitting a wall on data processing because the papers are incomplete, does the path to true reproducibility involve not just making the AI smarter, but using the AI's struggles to force us to be better? Could the push for 100% automated code generation actually lead to a future where researchers have to write incredibly precise, detailed instructions about data handling just to satisfy the AI? Are we moving towards a world where the AI isn't just coding for us, but it's also teaching us how to write better, more complete science in the first place, just by highlighting where our own descriptions fail? You have to wonder, is the AI showing us its limitations or ours?